Look at almost any link you click today. It is usually a massive string of text packed with tracking codes, marketing parameters, and deep link pathways. But when you run that exact same string through a shortener, all of that data collapses into a clean 6-character link. Instead of shrinking the target web page itself, the system functions as a high-speed digital locator. Executing that swap requires a logistical network to match your click to the correct destination, completely invisibly, in a matter of milliseconds. This diagram shows the simplest possible architecture to make that happen. It starts when your browser sends a creation request containing the long URL to a central server. The server's immediate job is to generate a unique identifier. This is a random string of characters mathematically guaranteed to never match any other code in the system. Once generated, this tiny string becomes the permanent alias for your massive original link. To keep track of this, the server opens a connection to a database and saves this exact pairing in a 2-column table. While this single server setup works for a few users, its simplicity hides a structural fragility that threatens the entire operation. We can see that fragility when we look at the execution phase. When someone actually clicks your new short link, their browser first contacts our shortening server. This forces the database to rapidly scan through its massive archives of records to find the perfectly matching long URL. This logic flow illustrates the response. Instead of loading the web page directly, the server issues an HTTP redirect, a command telling the user's browser to automatically load the actual destination web page. The server is acting as a traffic cop. It must receive the click, search the records, and issue the redirect command for every visitor, creating an immense processing burden. Now imagine a celebrity tweets your short link to millions of followers. Suddenly, an instantaneous, massive wave of global requests hits that single, fragile architectural setup at the exact same moment. The server's processing power and memory max out immediately as it tries to open hundreds of thousands of simultaneous connections. Underneath it, the database strains as it attempts to execute thousands of simultaneous search queries per second. The database eventually locks up from the massive queue of unfulfilled requests and stops responding to the server entirely. On the user's end, the browser sits loading until it returns a timeout error. The link is broken. A viral success on a single server is mathematically indistinguishable from a cyber attack. To survive this massive wave of traffic, network engineers must completely rethink and rebuild the core hardware structure. This diagram shows the first solution, spreading the incoming traffic. A load balancer sits at the front, dividing the wave of clicks across an army of duplicate API servers. This horizontal expansion ensures no single machine handles enough volume to reach its breaking point. To fix the bottleneck, engineers insert a caching layer, a lightning-fast temporary memory storage. The cache stores popular lookups. When millions click the same link, the cache answers instantly, bypassing the main database. By combining intelligent traffic routing with rapid memory storage, engineers successfully transform a fragile choke point into an incredibly resilient system that can withstand sudden viral spikes. This final diagram reveals the fully scaled global architecture working in harmony. We have moved from a single overwhelmed server to a distributed data flow that can route millions of simultaneous users without dropping a connection. These structural principles, load balancing, caching, and redundant databases, are what allow major tech giants to keep the internet running smoothly. Every time you click a tiny link, your browser initiates a sequence that spans load balancers, memory caches, and database clusters to reach its destination in milliseconds. If you want to continue exploring the hidden logic of system design, follow for our next engineering breakdown.